Welcome back. We were discussing in Fundamental of Electronics about the Zener diodes. We saw the Zener diode use as the voltage regulator. Let us see what is the meaning of second approximation of Zener diode. Although the second approximation we have already covered for the diodes in the previous lecture. The second approximation includes a Zener resistance in series with an ideal battery. So we have seen in the previous lecture that when you have a Zener diode, then that can be replaced with a battery with the internal voltage as Vz denoted by Zener voltage. However, if we add the second approximation, then we need to include one resistance which is known as the Zener resistance. In that case, the total voltage across the Zener diode now will be the summation of the Zener voltage plus the drop which is there in the resistance Rz denoted by the Zener current multiplied with the resistance of the Zener diode. If we take this diode to be ideal in case, then you need not to consider the resistance of the Zener, and hence the voltage drop will also be 0 to be considered for the ideal diode. Then the total voltage will be equal to the Zener voltage, where Zener voltage is nothing but the breakdown voltage. Let us see this effect on the load voltage. So previous lecture we have seen the use of Zener diode as voltage regulator, where the Zener diode is connected to the power supply whose output is Vs and there is an internal resistance Rs. We connect a load at the output, that is RL, and the voltage across the load is VL. So for the ideal case, the load voltage VL is equal to the breakdown voltage Vz. So whatever the breakdown voltage we have for the Zener diode, that is same as the load voltage because both are in parallel. However, if we include the second approximation to include the resistance Rz in series with the battery Vz, then the total load voltage will now be Vz plus Iz into Rz. Now the voltage across the load VL will be in a summation of these two voltages, which is Vz plus the total drop across the Zener resistance, where Iz is nothing but the Zener current which is flowing through the Zener resistance. So the change in the load voltage that we observe from the ideal case is nothing but the drop across the Zener resistance. Usually this Zener resistance is very small, resulting in a minor voltage change. About 1/10 we can consider of a volt, and hence can be neglected. So a certain example, it can be like if the Zener current is 10 milliampere and the Zener resistance is 10 ohm, then what is the voltage drop across the Zener resistance? So you will have 0.1 volt. That is the multiplication of 10 milliampere and 10 ohms. What is the effect of ripples on the Zener regulator? So ripple, we have seen that AC voltage variation that is superimposed over the DC output voltage. So basically we need ideally the DC output voltage, but there will be some amount of AC component present which will be superimposed on DC, that is known as ripple. So we will see what will be the total output voltage across the load resistor when you have the ripples present, and the equivalent circuit to analyze this ripple. So you have the input voltage coming from the source. This is the internal source resistance and the Zener resistance. Load resistance is connected in parallel. So if we remove this load resistance with open circuit, then we have the voltage which is VR out. Then three resistances will affect the ripple: the resistance of the Zener diode, the series resistance, and the resistance of the load. So these three resistances will affect the total ripple of the Zener regulators. For simplification purpose, we can typically think that the Zener resistance is very less than the load resistance. So the voltage divider equation we can use, where with the output ripple voltage we can calculate as the distribution of the voltage. So Rz divided by the total resistance, which is summation of Rs plus Rz multiplied with the input supply. These approximation for troubleshooting, when we need to do some design, then Rs is significantly greater than Rz. So if Rs is very high, then we can neglect this Rz in this equation, and we can say that the voltage across the load can be taken at Rz by Rs into VREP. Let us see one problem. So we have a linear diode here, which breakdown voltage is given to be 10 volt, and the resistance of the linear is 8.5 ohms. We have to apply the second approximation to determine the load voltage when the linear current is 20 milliampere. So the voltage which is dropped in the load RL, and here we have the resistance RZ which is connected in series with VZ. So IZ into RZ will be the drop. It is already given 20 milliampere as IZ, and RZ is 8.5 ohms. So we get 0.17 volt as the change in the load voltage. Now the load voltage using second approximation, we have the VL as the VZ value plus the total drop. So we get 10.17 volt as the total voltage across the load resistor. Second point of the problem, what is the approximate ripple voltage across the load? If given the source resistance is 270 ohms and the linear resistance is 8.5 ohms, input voltage is 2 volt. So we have seen the formula for VR out, where we have the resistance of the linear diode, which is 8.5 ohms, divided by the source resistance, which is 270 ohms, multiplied with the input voltage, which is 2 volt. It gives 63 millivolt as the ripple voltage. Linear dropout point and worst case condition, we will see when the linear regulation condition has to be achieved. If we want proper regulation, the linear diode must remain in the breakdown region. So the function of linear diode is proper only when it is operating in the breakdown region. There must be sufficient linear current for all the source voltages and the load current. So whatever the load current is flowing, so the linear diode should have a sufficient linear current for all the source voltages. So source voltages can be variable. So for these worst case scenarios of the linear regulator, so this is the linear regulator circuit, where if we decrease the source voltage, what will happen? So the source voltage, which is 20 volt, and the internal resistance, which is 200 ohms. So the current which is coming from the source or the series current is nothing but Vs minus Vz by Rs, change in the voltage by the resistance, given to be 50 milliampere. Load current is 10 milliampere and linear current is 40 milliampere. So if the source voltage is decreased, which we are taking into consideration, from 20 volt to 12 volt, so here the source voltage will be dropped from 20 volt to 10 volt. The source current will reduce to 10 milliampere and the linear current will be 0. So there will not be any Vs drop, and hence the regulation will be lost. So worst case scenario we are discussing, where we are discussing the source voltage reduce, so the regulation will be lost. Second case we will discuss if there is a decrease in the load resistance. So there is a load resistance RL. If it is decreased from 1 kilo ohm to 200 ohms, what will happen? Load current will increase to 50 milliampere and IZ will drop to 0. So again the regulation will fail when the load resistance is too low. So we cannot do load resistance too low, or we cannot do the decrease in the source resistance. Both will cause the regulation to lost. Now third resistance what we have is the series resistance. If we increase it from 200 ohms to 1 kilo ohm for an example, then IS will be reducing and again the regulation will be lost. So these resistances plays an important role in the regulation of the linear diode circuit. What is the formula to determine the maximum series resistance? So the resistance which is connected internally, what should be its maximum value? To avoid the failure under the worst case condition, the maximum resistance that can be considered in the circuit is given by the source voltage Vs, whose minimum value we take it, divided by the linear voltage minus 1 multiplied with the RL minimum value. So we take the RL value to be minimum. Then we can get what is the maximum value of the resistance that we can put in series. Alternatively, we can say that Rs maximum is nothing but the difference of the voltage from the source minimum value minus the linear voltage divided by the maximum amount of the load current. So either we can calculate from the load current or we can calculate from the resistance of the load. So these two formulas we will see in terms of a problem where a linear regulator has an input voltage that can range from 22 to 30 volt. So this is the voltage of the input which is changing. Given that the regulated output voltage is 12 volt and the load resistance changing from 140 ohms to 12 kilo ohm, what is the maximum permissible series resistance. So we have seen that Rs max will depend upon the resistance of the load and the voltage of the source by Vz. So we can find that to be 117 ohms. The question where we can use this formula where the Zener regulator has input voltage ranging from 15 to 20 volt and the load current varying from 5 to 20 milliampere, 0.8 volt. What is the maximum allowable series resistance? So here we can use this formula to find what is the maximum series resistance. So 15 volt is the minimum value of the input voltage minus what is the Zener voltage and divided by what is the maximum amount of the load current. So that gives to be 410 ohms as the maximum resistance of the series circuit. So Zener diode will have some maximum power and current which we can determine as the dissipation given by power dissipated as the product of Zener voltage into Zener current, and these powers does not exceed the Zener diode power rating, otherwise the Zener diode will burn out. So generally it will be in the range of 0.25 watt to 50 watt. So you cannot exceed this maximum power in the Zener diode. Similarly, if we want to determine what is the maximum current that can be flown through the Zener diode without exceeding the power rating, so whatever the power is lost as the maximum Bzm divided by the Zener voltage, that will give what is the maximum current that can flow to the Zener diode. Now there is a concept of load line analysis which we have already covered in normal diodes, general purpose diodes. But what about the Zener diode? So let us understand with the help of one circuit where you have a source, the Zener diode and the internal resistance. So the current which is flowing through the Zener diode is given by Vs minus Vz by Rs in accordance with Ohm's law. And we take an example where the source voltage is 20 volt and the internal resistance is 1 kilo ohm. Then the Zener current will be 20 minus Vz by 1000. Now there are two important points that we have to take. One is the saturation point and another is the cutoff point. Saturation point is the point where the Zener voltage will be 0 and cutoff point is the point where the Zener current will be 0. So in this equation, we want to find the saturation point when the Vz is 0, the Zener current will be 20 milliampere. So first we have to put this value as 0 volt and find out what is the Zener current. In the second case, we have to put this one as 0 ampere and find the Zener voltage. So these points, like first point we are finding voltage 0 and the current is 20 milliampere. And in the second case, we are finding the voltage to be 20 volt and the current to be 0. So we will be using this to plot on the VI characteristic of the Zener diodes. So we will be getting one straight line connecting the two important points. Now, if the source voltage is 20 volt and the resistance is 1 kilo ohm, then there may be different points. So we can have different points here and we can connect it under different conditions. And this is the normal graph of the Zener diode VI characteristic. So where the point is cutting the straight line which we obtain, that is the quiescent point, and this is basically known as the load line analysis. So we can find out the Zener current which is flowing in the circuit and determine the difference Q1 and Q2 points. So we can find that the Zener diode will maintain nearly constant voltage despite the change in the source voltage. So even you change the source voltage, the Zener diode will remain a constant voltage operation even we change the source voltage. So this is about the load line analysis, which is on the similar line of normal diodes. So we have seen some of the fundamental concept of Zener diode voltage regulator and the load line analysis. This is from the special purpose diode topic. We will continue this with other type of diodes also, like the LED diodes, pin diode, tunnel diodes, and so on. Thank you for now.